Okay, let's start today's lecture. In the last lecture, we were discussing about the shift registers, and so far we have studied about serial in, serial out, and serial in, parallel out shift registers. Two more type of registers are parallel in, serial out, and parallel in, parallel out. As far as registers are concerned, we have discussed about the registers are used for temporary storage of the data in your processor and for movement towards left or right of the data into the register. Now in today's lecture, we are going to discuss about parallel to serial conversion, or we can say we are using parallel in and serial out shift register, that is PISO. So the block diagram of parallel in serial out register, we have this is input Y, which is parallelly in into the register, and data is fetched as a serial. So we can also say that it is a parallel to serial conversion. Suppose we are using a pen drive and we are fetching a data from a storage device in your storage location in your computer. Now as data is stored in the parallel mode in the computer, and when we are using a serial USB port, that is universal synchronous bus, so what it happens, the data is fetched serially, means one bit at a time is fetched from the hard drive or any location in your computer, and it is fetched or stored into some other location. So in this way we use parallel to serial conversion. So data is fetched parallelly, that is data is loaded parallelly, but it is out serially. We have a preset control, we have a clear control, and we have a shift pulse. The shift pulse is nothing but your clock pulse. So we, for the conversion of parallel to serial conversion, we use a parallel in, serial out shift register. The data is applied in parallel form to the parallel inputs pin PA to PD of the shift register. This is PA to PD is nothing but the flip flops we have named as A, B, C, D. We are using 4 flip flops, and P stands for parallel in. So this is the way general block diagram. So here we have used 4 flip flops. So it is a 4-bit parallel in, serial out shift register. It is then read out sequentially from the register 1 bit at a time from PA to PD on each clock cycle in the serial format, as we have done in the serial in, serial out register. For a 4-bit serial in, serial out register, we require 4 clock pulse to fetch out the data, and we can say in general that to load a data a single clock is required, so that with a single clock all 4 bits are loaded into the register, and when we are fetching the data, that is unloading the register, it requires 4 clock pulse. So you can say that it requires 1 clock pulse to load and 4 clock pulse to unload, and as compared to the serial in, serial out register, it was requiring 4 clock pulse to load the data and 4 clock pulse to unload the data. That is overall 8 clock pulses are required for a serial in, serial out shift register. And as compared to that particular register, here in case of the parallel in, serial out, we require 1 clock to load the data and 4 clock pulse to unload the data. That means we are having only 5 clock pulse to load and unload the data. So here you can see directly that the connections are same. We are using D flip flops. So DA, DB, DC, and DD. These are the 4 flip flops, and the inputs are PA, PB, PC, and PD. So here A, B, C, D, and we are the output is connected in the same way. So whenever a single clock pulse is given, that is the active clock is given to the flip flop, whatever is at the input of the flip flops, that will be entered into the data and will reflect at the output. And to unload the data, we require 4 clock cycles, so that 1 bit is out from the register for each and every active clock pulse. So whenever there is an active clock pulse, a data is out serially. The first data will be D, that will be out. Then this data C, B and A. In this manner, we can read out the serial data. Further, parallel out shift register, and the last one, as we have discussed serial in SISO, SIPO, PISO, and PIPO, that is the parallel in parallel out shift register. So it can serve as a temporary storage device or as a time delay. So data is entered parallelly. We have used 4 blocks, that is 4 flip-flops. Each block represents a flip-flop. Data is loaded parallelly and data is fetched parallelly. Data is presented in a parallel format to the parallel input pins PA to PD, A, B, C, D. These are the 4 inputs. Then shifted to the corresponding output pins QA to QD. So QA, QB, QC, and QD are the 4 outputs when the register are clocked. So one clock pulse is required to load the data and one clock pulse is required to unload the data. So comparatively, it requires only 2 clock pulse to load and unload the data. Hence, the speed of the PIPO shift register is very fast. So here are the connections. We have PA, PB, PC, PD, 4 inputs, and QA, QB, QC, and QD, 4 outputs. So whenever active clock is required, active clock is given to the all flip-flops simultaneously, synchronously. So data is loaded and data is with a single clock pulse, data is available at the output, and whenever required, we can fetch the data with a single clock cycle. Now there is another shift register, or it is a form of parallel in serial out shift register. Shift register with parallel load. We can load the data parallelly and we can shift it as well as. So here in this circuit, this particular diagram is nothing but it is a 2:1 mux. We have studied 2:1 mux when we were discussing combinational logic circuits. So here we have used a pin load oblique shift. So whenever load oblique shift is 0, so this line will be 0. So the all gates, all AND gates noted by 1, the output of all gates which are noted as 1 will be 0, because any input to the AND gate is 0, then the output of the AND gate is 0. Now we have used an inverter. So whenever this line is 1, so the out so 0, then the output of the inverter will be 1. So we can directly shift the data. This serial in data can be fed. This data is out from the first flip-flop and fed back to the next 0 number or 0 level of the AND gate, that will be shifted. So in this way we can do, that is serial in serial out shift register. On the other hand, if load oblique shift is 1, so the input of the all AND gate labeled as 0, as it is connected to the output of the AND not inverter. So whenever load oblique shift is 1, then the output of the inverter will be 0. So all AND gate have an input which are labeled as 0 will have an input 0. That means the output of all AND gate which are labeled as 0 will be 0. And now the all AND gate which are labeled as 1, so here it is 1, again it is 1, and here it is 1. So I have uses the n bit of shift register. So in this way, whatever is the input of the other input of the AND gate which is labeled as 1, that is 1D, 2D of ND, if we are using n bit of data, that will be reflected to the OR gate, and that will be reflected to the input of the D flip-flop. So in this way, we can parallelly load whenever active clock is given to the flip-flops. Whatever is at the input, that is 1D, 2D up to ND, that will be reflected to the D flip-flop, and wherever there is an active clock, the output will be according to the input. So in this way, we can load it with the parallelly, and after this, we can shift it serially. Whenever we put this again 0, and the data can be shifted serially. So this is a sort of a parallel in serial out shift register, or we can say a shift register with parallel load. which is capable of shifting serially, and that can take a data serially as well as parallel. There will always be a question in the examination regarding shift registers, and the high probability of the question is bidirectional shift register or universal shift register. So here we are going to discuss about the bidirectional shift register. As clear from the name, it is a shift register which can move data shift right and shift left. So bidirectional means in the both direction data can be shifted. A bidirectional shift register is one in which the data can be shifted either to left or to right. So the block diagram of the bidirectional shift register should be like this. The upper figure is for shift right and the lower block diagram is for shift left. So we are interested to design a shift register in such a way that which can shift data both, which takes data serially and can shift to the left hand side and to the right hand side both. That's why it is known as bidirectional shift register. So here we go. That is a conclusive design of this shift register. Again, we are using the same mux type. This G1, G5 and this OR gate becomes a mux. So we have used G1, G2, G3, G4. All one input of all gate is connected to the control input shift oblique left bar, and G5, G6, G7 and G8 are connected to, one input is connected to the output of the NOT gate. So suppose right oblique left bar is if 0, then the output of the NOT gate will be 1. So in that case, G5, G6, G7 and G8 will be activated. Whenever it is 1, then the output of the NOT gate is 0. That means the output of G5, G6, G7 and G8 is 0. And in that case, G1, G2, G3 and G4 will be active. So this is the design. So whenever, suppose left oblique shift bar, right oblique left bar is 1. Suppose this pin is 1, then output of the NOT gate will be 0. That means output of G5, G6, G7 and G8 will be 0. So all will be 0. Now in this case, the output of G1 will be whatever is the serial input data. Suppose it is 1 and another input is 1. So 1 here is 1. This 1 output of the OR gate will be 1. That whenever clock is active, whenever active clock is given, then this value will be reflected at the output. Again G2 is activated, this data will travel here to the OR gate, second flip flop, and then output is fed to the G3 and it comes through the OR gate to next flip flop C. Then the output Q2 is fed to the G4 and G4 is activated. This output, this will travel through OR gate and will go to the Q3. In this way, this is the operation shift right. Now suppose this value is 0. The right oblique left bar is 0, then the output of G1, G2, G3 and G4 will be 0. And in this case, G5, G6, G7 and G8 all AND gate will be activated because the output of the NOT gate is 1. And the serial data is fed here because this output of this gate is 0. This input serial data goes to G8. As G8 is activated, other input of the G8 is 1. This output will, the G8 input data will be at the output of the AND gate and it will travel through OR gate and it will be here. Now again, this input is fed back to here and it goes to G7. Now from G7, it comes to, whenever active clock is given, it travels from G7 through OR gate to the Q2. Now again, we can see that Q2 is fed back to G6. And whenever active clock is given, it travels from G6 to OR gate to Q1, and again Q1 goes back to G5. It goes from G5 OR gate. Then here is your data out, that is Q0. So in this way, depending upon the value of right oblique left bar, we can shift data to the left hand side and we can shift data to the right hand side. So whenever we are shifting right, the output will be at Q3. Whenever shifting left, the output will be at Q0. So in this way, we can travel or we can shift data in the both direction, to the left hand side and to the right hand side. That's why this is known as bidirectional shift register. So now, as we have discussed about shift registers and flip-flops, there is another type of adder, that is a serial adder, which is used as in a combinational circuit. We have studied half adder, full adder, parallel adder, carry look ahead adder. Now this is another type of adder when we are required to add a number serially instead of parallelly, because in parallel adder, if we are required to add 64 two numbers with 64 bits, as your processor size normally is 64 bit, so the all registers in the flip flop will be of 64 bit, and we to add these two numbers we require 64 full adders. That means the circuitry will be large, it will cost large, but the data will be added parallelly. That means it will take less time, because there is always a trade-off between time and the cost. Whenever you need a fast processor or fast processing in your digital, that means you have to pay more. Now another solution, when you are not bothered about the time, but you are you are interested to save the money, then we use serial adder as compared to the parallel adder, because the hardware requirement of the serial adder is very less as compared to the parallel adder. So here we can see the block diagram of the serial adder. Suppose our data is stored A in the, that is a 64-bit shift register A. A number A is stored in shift register A. Another number is stored in shift register B. So this data can be fed serially in. Now what we are interesting, that we are interesting to add two numbers A and B and store the result sum in the register A. So what we have done, initially we have loaded A and loaded B, either in serial manner or in parallel manner. What we have studied, four types of shift registers. There is a shift control, there is a clock. Shift control, it will decide it is a shift left or shift right. So forget about this circuitry. Let us come to the general operation. That is the shift register A. First bit will be A0 and the last bit will be A63. If it is a 64 bit, then it is B0 and B63. This is a full adder, so you can clearly see, instead of using 64 full adders as in the case of parallel adders, we are using only a single full adder. So a full adder has inputs X, Y, Z. X, Y, and Z, these are the three inputs. Sum and carry are the two outputs. So X and Y are two numbers, and Z, here we are using the previous carry. So what happens, whenever first clock pulse is given, then A0 and B0 will be serially out, that is serial out. It will go to X and Y, and the previous carry is initially 0, because we have used a D flip-flop. We have cleared this D flip-flop, and whenever this D flip-flop is cleared, that means output Q is nothing but output Q is 0. So we are adding A0 plus B0 plus 0, and it will produce a sum S0 and C0. So this S0 is again with a single clock pulse, it will be entered to shift register A. Or you can use another shift register here, and you can connect this S0 to the shift register. Whenever a clock is given, the data is input serially into the shift register. Now with the clock, next clock cycle, what happens? This C0 comes to the input of the D flip-flop, and whenever clock is given, because we are giving clock continuously, synchronously, shift register A, shift register B, and the D flip-flop all have common clock. So whenever next clock is given, so whatever this C0 will be at the output of the flip-flop. Now in this manner, we will adding A1, B1 and C1. So next clock pulse, next output will be S1 and C1. Again, this C1 is fed back with the next clock to the input ladder. So in this way, what we can conclude, sorry, we can conclude that with this very small and very least hardware, we can add n bit of data with n clock cycle, whereas on the other hand, as compared to the parallel adder, in the parallel adder we need not require any clock cycle. Whenever data is input to the full adder or the parallel adder, within a stimulated time of processing time, the output as the output will be available at the output of the parallel adder. But in this case, if we are using 64-bit of data, then we have to wait till the 64th cycle so that the output can be stored into the shift register. So when we compare a parallel adder and a serial adder requires less hardware, it takes more time. That's why the cost of the serial adder is less. As in case of the parallel adder, it requires large hardware, and that's with the large hardware speed is fast, but we have to pay more. That means the costing of the parallel adder will be high as compared to the serial adder. So this is wrong letter. This is basically a universal shift register, not the bidirectional shift register. It is a universal shift register. So here we have used 4 D flip-flops. Clock to the all flip-flop is common. We have used a clear pin, clear, so that the initial data is cleared into the flip-flop, and we have used 4 muxes. All the select lines of the muxes are common, that is our S0 and S1. These are the select line of the flip-flop. And now we come to the connection. So this universal shift register is capable of serial in, that is shift right, serial in for shift left, and it can be parallelly loaded, parallelly in, serial out, parallel in, parallel out, serial in, serial out, shift left and shift right. The all operations can be performed with the help of the single particular diagram. That's why it is known as universal shift register. Now come to the working of this particular shift register. This is the operation select lines S1 and S0, and these are the operations of the mux. Suppose select lines are 0, 0. So whenever select lines of the mux are 0, 0, then the output is connected to the first input. So the output is connected to the first input. Here output is connected to the first input. Here it is 0 into 0th input, 0th input. Now we can see that whenever this output is connected and this input of the mux is nothing but that is the output of the flip-flop. It is fed back with a loop. So we can say then whatever is the output of the flip-flop is the input of the mux, and this output of the mux is input of the flip-flop. That means it is nothing but it is a loop. That means whatever is the output of the flip-flop, that will be fed back to the flip-flop with the help of the mux, and we can say that the operation is no change. The 0, 0 operation is no change. Now suppose select line is 0, 1. Then the first, that is the next input labeled as 1 of the mux will be connected to the output, because mux acts as a switch. It is a 4:1 switch. So 1 is connected to this output, this 1 is connected to this output, 1 and 1. So in this manner, and the 1 is connected to, that is serial input for shift right. So whenever select line is 0, 1 and the active clock is given, whatever is the input, it is fed back from the mux to the D flip-flop, and it will be at the output. Now this output is connected to, because this line is deactivated, it is connected to 1 to the next mux, and it will go to A2. Then this A2 goes to the next mux, go to next flip-flop, that is A1, and A1 is connected to the next flip-flop, and it goes to the A0, and hence we can find out from A0 that 4 clock cycle, the 4 bit of data can be entered and it can be shifted to the right side. Provided that the select line positions are 0, 1. So we can say whenever select line positions are 0, 1 and we give an active clock to the all flip-flops, the data is shift right serial in. Again, now suppose the select line are 1 0. Whenever it is 1 0, then the input number 2 is connected to the mux and it is directly connected to the D flip flop. Now with the input 2 of the mux, we have serial input for the shift left. Now let us see what happens. It is connected like here. 2 is connected to the D flip flop, and the whenever active clock is given, data is at the output A0. This A0 is now connected to the next mux, goes to A1. Now A1 is connected to next mux and goes to D flip flop, then A2, and A2 is connected to the third input of the mux, then it goes to A3, and we can find out from here A3, whenever we are giving continuous clock cycles, that the data can be fetched from the A3 serially. Now in this manner, we can see that this is shift left. So data is shifting to the left, as we have studied in the bidirectional shift register. Now suppose in the last case, if the select lines of the mux are 1 1, then we can see that the third, that is the last one input of the mux is connected to the D flip flop. So this is nothing but I0, I1, I2, I3. These are the parallel inputs. Whenever single clock cycle is given to the flip flop, data is loaded parallelly. And in this way, if we have to find out the data parallelly out, so data is available with the one clock cycle at the output A0, A1, A2, and A3. And further, we can shift this data either into serial. Once we have loaded the data into the flip flop, we can serially we can shift right or shift left depending upon our requirements. So this is the way how the universal shift register works. So so far we have discussed 4 types of basic shift registers: serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. Further, we have 2 different combinations of the shift register. One is bidirectional shift register, and this one we have universal shift register, which are capable of different type of functions for the shifting left, right, and to the parallel load and parallel output. Now another interesting shift registers are the shift register counters. Many times this question has been asked in your sessional examination or the main university examinations. These are the shift registers, but uses as the counter. Counter is nothing but which can count anything. So shift registers can form useful counters by recirculating a pattern of zeros and ones. And for this purpose, we have 2 important shift register counters, which are known as Johnson counter and the ring counter. So first, let us discuss about the Johnson counter, which can be made with a series of D flip flops, and the arrangement of the flip flops are like this. It is nothing but a serial in, serial out type of shift register, but the output Q3 bar, that is the complementary output of the last flip flop, is fed to the as input to the first flip flop. And what we have done, we have cleared the flip flop, that is initially output of the flip flop is 0 0 0 0, means Q0, Q1, Q2, and Q3 are 0 0 0 0. That means Q3 bar will be 1. So this is the way how a Johnson counter is constructed. Further, we can construct a Johnson counter with the help of the JK flip flop, but it is advisable that always you are represent Johnson counter or ring counter, you have to construct with the help of the D flip flop, because it is the simplest one method. So this is with the help of the JK flip flop. Again, the same has been done. Q3 bar is as the input of the J0. And here the Q3 bar is the input to the D0. Now redrawing the same Johnson counter without the clock showing illustrates why it is sometimes called as twisted ring counter. So we can say the Johnson counter is also known as twisted ring counter, and when we redraw the circuit, it looks like that. I have removed clock here, and you can see here is the twist, because Q3 bar is connected to J0 and Q3 is connected to the K0. You can see in the previous slide, Q3 bar is connected to J0 and Q3 bar is connected to the K0, and all connections are straightforward. Q0 equals to J1, Q0 bar equals to K1, Q1 equals to J2, Q1 bar equals to K2, like this. So here is a twist in the uh, connection. That is why it is known as twisted ring counter. So whenever working comes to the Johnson counter is useful when we need a sequence that changes by only one bit at a time, but it has limited number of states. Suppose the first 5 counts of a 4-bit Johnson counter that is initially cleared. So what we have done initially, the output of the flip-flop is 0 0 0 0. So here it is 0 0 0 0 with a initially, that is clock 0. Whenever first clock is given, because Q3 bar is input to the D0. So Q3 bar, as Q3 is 0, the Q3 bar will be 1. With the next clock cycle, 1 will be transferred. And this will be here, this will be transferred here, this will be transferred here. Again, with the next clock cycle, still Q3 bar is, because here Q3 is 0, that means Q3 bar will be 1. So 1 will be fed into Q0. So 1 is here, this 1 comes here, 0 and 0. Now again, still Q3 is 0. That means Q3 bar is 1. With the next clock cycle, this is 1 comes here, this 1 comes here, 1 comes here, and 0 comes here. Again, Q3 is 0. Some network issue. Now suppose we were discussing Q3 is still 0. That means Q3 bar is 1. With the next clock cycle, 1 comes here, 1 comes here, this 1 comes here, and Q3 bar comes here. Now there is an exercise for you. What are the remaining 3 states? You have to do yourself. Now what will happen? This Q3 is 1. That means Q3 bar will be 0. Now in the 5th clock cycle, you see 0 will be here, 1, 1 and 1. So the output of the 5th clock cycle will be 0, 1, 1, 1. With the next clock cycle, output will be 0, 0, 1, 1. With the next clock cycle, it will be 0, 0, 0, 1. With the next clock cycle, it will be 0, 0, 0, 0. Now this states comes. So we can see we are using 4 flip-flops, then 2 n states are there. Means 8, after 8 clock cycle, the counter will repeat its cycle and it will move in the loop. So this will be an exercise for you to find out the next remaining 3 states. You can do yourself and you will find out that after 8th clock cycle, the system will repeat all its states. Now the another arrangement is the ring counter. That is the last topic of the shift registers. The ring counter can also be implemented with the help of either D flip-flop or the JK flip-flop. So here is the arrangement with the D flip-flop, and you can notice the feedback. So the only difference is there that here Q3 is input to D0 instead of Q3 bar. This is the only difference in the feedback. And in the same way, you can construct it with the help of D flip-flop. Same arrangement is here. But what you have to do, initially you have to clear flip-flop D0, D1 and D2. Then the output of these flip-flops should be 0. And you have to preset flip-flop D3. That means the output of the D3 should be 1, so that that particular loop can be obtained. The redrawing the structure without clock, you can see it forms a ring. That's why it is known as ring counter. The disadvantage to this counter is that it must be preloaded with a desired pattern, usually a single 0 or a 1, or single 1 or a single 0, and it has even fewer states than a Johnson counter, because in Johnson counter we have 2 n states. On the other hand, it has the advantage of being self-decoding with a unique output for each state. So we can see the timing diagram. Now a common pattern for the ring counter is to load it with a single 1 or a single 0. So what I have done, that initially Q0 is 1 and the rest of Q1, Q2, Q3, Q4, whatever are the flip-flops are 0. So suppose we are using Q1, Q0, Q1, Q2 and Q3. If we are seeing with a 4-bit pattern, it is a 8-bit ring counter. The output is for the 8-bit ring counter. So I have made Q0 is 1, Q1, Q2 and Q3 are 0. So what happened with the first clock cycle? Q3 is 0, that Q3 is fed to the D0. So the output of D0 is 0. This one transferred here. Again in the next clock cycle, 0 comes here, 1 comes here, and this one comes 0 comes here. So in this way you can find out that after 4 clock cycle it will repeat its state. So we can directly see in case of the Johnson counter we have 2n states, and in case of the ring counter we have only n number of states. So you can in the same way you can find you can construct the table of the states, putting Q0 as 1 and the rest of the inputs, rest of the outputs as 0, or you can see the Q0, Q1 and Q2 as 0 and Q3 as 1. So because you have to preload only single one and the rest of the output should be 0. In the same way you can find out the output of the flip-flops, and you will see that it will move, it will repeat its cycle after 4 clock cycles. So let us stop our topic here.